In the previous part of this lecture, we have extended the link checker example to run on a cluster of nodes, and we have seen that cluster start up and shut down. But how did that actually work? What were these states which we have seen? When a cluster node wants to join, it enters the joining state. That was the first one we have seen. We have also seen that in the example nothing happened until the second node joined, because we had defined that the cluster needs at least size 2 to work. But what happened then is that the node became up. This transition was made by the leader when the leader determined that all members of the cluster had seen all new nodes joining. When the program was done, the cluster main shut itself down, and it did so by declaring that it wants to leave the cluster. This intention is expressed by going to the leaving state. This transition can be done by any node without the leader having anything to do with it. The information that the node wants to leave needs to be disseminated to all others so that they are prepared to remove it from the membership list, because otherwise not all would have the same picture and it would not be a cluster. In order to do that in an orderly fashion, the leader determines when all have seen and moves the node to the exiting state. This is the signal for all the other nodes to remove this entry from their membership list at their next convenience. This was the sequence of states which the cluster main went through, from joining to up, then performing what it was supposed to do, and then leaving via this path until it shut itself down. The cluster worker left the cluster afterwards by a little bit different route, which was via a state called unreachable. And we'll talk about that next. In order to form a cluster, everyone within it needs to be in consensus about who is in it. That was the definition of it. Therefore, only if the members of the cluster can communicate with each other can the cluster function. This means that the reachability of all cluster members must be closely monitored, and once one becomes unreachable, special action needs to be taken. In order to check the ability to communicate, every node in a cluster is monitored by several others using so-called heartbeats. That means that periodic messages are sent, and once they are not received anymore, there is presumably a problem. Now, if you have a very large cluster, it is impractical to have everybody monitor everybody else, because then the number of connections needed for that, the number of communication pairs, would be roughly 1/2 n squared, which can be a lot. Therefore, we apply a technique of that the neighbors monitor each other. How do we define neighbors? Let's say we have a cluster with 7 nodes. 1, 2, 3, 4, 5, 6, and 7. Since these nodes all agree that they are the 7 which are in the cluster, and you can apply a sort order on their addresses, every of these 7 nodes can draw the same kind of ring with the same order of the nodes in it. And then we could say that 1 monitors 2 and 3, 2 monitors 3 and 4, and so on. This would be a picture if every node would monitor 2 others. For a more tight mesh, we could also make it 3, for example, then it would look like this. Let us say that node 5 fails. It was monitored by 2, 3, and 4. Eventually, these 3 nodes will not receive heartbeats from 5 anymore, but heartbeats cannot be sent at a 1 millisecond interval. That would just be too much. So let's say you send a heartbeat every 5 seconds. Then within 5 seconds, the 3 will notice that the first heartbeat was not received. But that might just have been a fluke. The next one might still arrive. So triggering when one is absent is usually too finicky. So what you need to wait for is that 2 or 3 fail, and then it takes maybe 15 seconds. And the more monitors you have, the higher the chance is that you get the signal a bit earlier. So let us say node 4 was the first to detect that 5 is down. Then this information will be included in the gossip messages. And 4 talks randomly to all the other nodes in the ring and spreads the information. So it might be communicated to 6 and then to 2, but 6 also keeps talking to 1, and so on. And eventually all of them will know that node number 4 has seen that 5 is down. For a cluster to be hampered in its function, it is enough that one of the communication links does not work, unless messages can be routed via other nodes. So if 4 and 5 cannot talk anymore, and if, for example, the routing protocol does not allow messages to go via 1, for example, then the cluster cannot function. And that is the case in Akka, that supports only direct messages at this point. This means that as soon as one node sees another node as unreachable, that node has to be considered unreachable for the whole cluster. And that means that the cluster currently is inconsistent, because these 6 nodes think that that one is not part of the cluster. But this node, well, it might not have crashed. Someone might have pulled the network cable out from it, so it cannot communicate anymore. And the last state that it has is that everybody is part of the cluster. But as this node is also monitoring other nodes, namely 6, 7, and 1, it will conclude after some period of time that they are down. It will start monitoring these instead to see if they are still up. So in the end, the clusters will split. 5 would be in a cluster on its own, and these nodes would also be in a cluster on its own. But in order to form these clusters, nodes need to be removed properly, so that these 6 nodes can declare that 5 is no longer in it. Going back to this state diagram, unreachability is not really a state, it is a flag, because a node can become reachable after a period of time. For example, someone plugs in that network cable again, and everything happily starts over. But unreachability is important enough to be part of this diagram. And nodes can become unreachable at all times, at any time. And if the nodes did not really crash, as I said, they can become reachable again. In order to form a new cluster without the unreachable node, that node needs to be communicated that it is leaving. But it is not the same kind of leaving as we've seen over here, because the node went down. This transition here is a policy decision, because you cannot in all cases say whether the node is really down or whether it is transiently unreachable, whether it will come back. So in the end, there will be some either a program or an operator monitoring the system and deciding after which unreachability period to move a node to down. Once that has happened, and once that has properly been disseminated among all the remaining cluster nodes, the leader removes the node. Now we can recapitulate the whole history as seen by the cluster worker. It was joining, it saw the main joining and then up. And once the main program stopped, the cluster worker detected it as being unreachable. Then I have shown you that I set an option called auto down in the worker, which means that as soon as a node becomes unreachable, this transition happens automatically. So as soon as the failure detector flagged that the main is unreachable, it went from up via unreachable to down. And that means that there was just one node in that cluster left. The cluster worker was the only node and therefore also its leader, and it removed the main, and that triggered the cluster worker's main actor to shut down the program. In the program code, we registered for certain events to be received. The first one was member up, and that is published exactly with this transition here. And in response to it, we started the program running. The cluster main reacted to this member up event in order to start the calculation. The cluster worker was more interested in when the main exited, and that is published as member removed upon this transition here, as well as this one. There are other transitions which you can listen to, for example, member leaving and member unreachable, which were not shown in code so far. Whenever a node is removed from the cluster, all the actors which are on it might still be alive if it's just a network partition, but that does not matter. As far as the cluster is concerned, this node is removed and does not exist anymore. That also means that all actor refs which are still held within the cluster to actors on that removed node need to be considered terminated. If, for example, Deathwatch was registered on these actor refs, then the terminated messages must be delivered, even though the actors possibly have not really stopped yet, but they are considered to be dead after the node has been removed. This is important to allow consistent cleanup of resources. One actor monitoring the life cycle of another was interested in when that other actor cannot perform its duties anymore, and that is clearly the case here. Another reason why this needs to be done consistently is that for remote deployed actors, for example, if a child actor was on the removed node, the parent needs to be told that that child is no longer there, the name is free again, for example. Or if that node had remote deployed children to nodes which are still on the cluster, then these are currently without a parent. And that cannot be, because then there is no one who will handle their failures. This means that they also need to be stopped. The most important part of the semantics of Deathwatch are that once the terminated message has been delivered, no further communication will be received from that actor. This has consequences on the cluster as well. Once a node has been removed and Deathwatch has fired on all the actors within it, this node cannot join the cluster again. It cannot come back, because that would mean that the actors could also start sending messages again, and that would violate the contract of the terminated message. Therefore, a node which was removed from the cluster needs to be restarted completely before it can join again, and there cannot be any of the old actors still on it. If you have paid close attention, you will have noticed a small inconsistency here. In Akka, message delivery is not guaranteed, but still we do guarantee that the terminated message arrives. The need for this guarantee should have become clear, And the reason why we can afford to implement this guarantee is that terminated can just be synthesized. It can be put together even though the sender is currently not able to do that anymore. Therefore, the terminated message enjoys this special status. To try this out, we will modify the cluster worker not to rely on the member removed event, but instead to use DeathWatch, so that it terminates once the cluster main stops. First of all, the worker needs to subscribe to the member up event, and after joining the main, it waits for this event to arrive, signaling that the cluster main has been started. Then we need an actor to which we can apply DeathWatch. We know one which will exist, that is the receptionist. We can construct the receptionist's actor path because we have the main address and we can form a root actor path from it. And then these paths have a little DSL built in where you can separate by slashes the path components. So this is the address of the cluster main /user/app/receptionist. We can resolve this actor path using actor selection and sending it an identify message with some random tag here. And if we cannot resolve the receptionist, something must be wrong. We stop the program. Otherwise, this is the normal case. We just watch the receptionist, and once we get the terminated, we stop the program. You can see here this modified cluster worker. I've inserted one log line when we successfully watched the receptionist to print out who that was. Now running the program. We see that the main program performs its duty. It did the retrievals and then it shut down. But we are more interested in the worker. We see here that the worker was welcomed into the cluster by the cluster main. And then we resolved the receptionist to be this actor ref here with the UID. This was at 11:09:21, and then 8 seconds later, when the work was done, the application was shutting down because it received the terminated message. As you have seen, using the cluster is really not complicated. It just means subscribing to some events and then reacting to member up, and for example using DeathWatch just as normal. I invite you to play around with this program a little bit, maybe add more cluster nodes and see how you can make this program scale.